Okay, so welcome to the talk on thermodynamic degradation science. I'm Dr. Alec Feinberg. Uh, I do consulting training and have reliability software that you can get at the website down here. Um, and there's my email or contact information, and I'd be glad to answer questions regarding the seminar. and I appreciate everybody taking their valuable time out of the day to come to hear the talk. And I know people are very busy, so it's nice to see we have a pretty good audience for this. So thank you again, and thank you to ASQ for giving me the opportunity to present the work that I've done in this area. So just a little bit about a little bit more about myself is that I don't work in academia. I've been in industry, so I've tried to focus on a practical area, the practice of thermodynamic degradation science. It's been kind of a hobby of mine because obviously in industry you can't always do this kind of stuff. So only recently, when I became a consultant, had more time, did I was able to put the book together. So the first paper I started writing on this was in 1995. So not that it took 20 years to write the book, but it does take a while for things like this to evolve. And I mean, I could have called it something to do with physics of failure, maybe a more popular topic, but I just really felt that it is its own science and it deserves a place all in its corner by itself. So that's where the name sort of came from. So this is a summary talk that I'll be giving at RAMS, and it's likely to run over in an hour. Here's a table of contents. We'll start off with basic concepts in thermodynamic science. Um, Understanding thermodynamic work and how it relates to degradation. Selected physics of failure models rather. We'll be talking, then we'll talk about a subject that I call mesoscopic noise entropy measurements, and final thoughts that I call the theory of organization. So here's my notation for the talk. If it's a physics of failure aging law, it's highlighted in red. If it's a key physics of failure statement, it's dashed line in red, and examples are in green. Section 1, basic concepts in thermodynamic degradation. So just to categorize physics of failure modes, we can right away we can start talking a little bit thermodynamic terms. We use the word irreversible. The irreversible mechanisms of interest that cause aging are categorized into four main categories: force processes, activation, diffusion, and combinations of these processes. So aging, depends on the rate controlling process, obviously. So any one of these processes can dominate, or they can all participate and cause this complex aging. So those are the key driving forces on that. So where does thermodynamics come into play, and why are we rattling about it? It really comes into play about the second law, because the second law kind of explains perfectly why things age. So in terms of, we can rephrase the second law in terms of the second law of thermodynamics in terms of aging, and we would have to use the thermodynamic dot the i's, cross the t's kind of stuff. So we call it the spontaneous irreversible degradation processes causing aging that can take place in a system interacting with its environment will do so to go towards thermodynamic equilibrium with its environment. So we begin to see where thermodynamics plays a role, because its second law tells us that things want to come to equilibrium, and that's what's driving aging. Now, in thermodynamics, we divide things up into the system and its environment. So the system is some sort of volume set apart for study. So from an engineering point of view, it's the concern of possible aging that can occur when we talk about physics of failure. The environment is the neighboring matter which interacts with the system in such a way to drive it towards that equilibrium. So it's that interaction between the system and the environment that drives the system towards the thermodynamic equilibrium, which is its lowest energy aging state. So we want to be careful, because there's a lot of people in reliability, so I don't want to confuse them. because the term system is different in thermodynamics. So in reliabilities, a reliability system is complex. It usually has many components, but not on the same level. The thermodynamic system uh, is a volume set apart for study. It could be simple like a resistor or complex like a reliability system. So that's your little warning. And sometimes I interchange these so I can talk about complex systems. So I think maybe you just need to define it, whatever you're talking about. Now, I'll next introducing the concept of entropy and entropy damage so we can start to see where thermodynamics has its strength in the aging situation. So entropy S is a measure of disorder. Entropy damage is a measure of permanent disorder. So there's a new concept that is in my, or a new term that's in my book called entropy damage. So we're going to talk about that a lot. So we can write the second law in entropy terms. So let's rephrase it now in terms of entropy. So basically what we're saying is that when things age, they're getting more disordered. So that's where entropy has its strength, is that there's measurements, ways to measure entropy and to understand the disorder that's occurring. So in terms of entropy, the spontaneous irreversible damage processes that take place in the system, environment interaction, when left to itself, increases the entropy damage, which results from a tendency of the system to go towards thermodynamic equilibrium with its environment. So that's another way of saying the second law by rephrasing it in that way. There's lots of different ways of phrasing the second law. Some people say, oh, the second law just means the entropy of the universe is increasing or something like that. So I guess I don't think in that big of terms, but I really like to talk about a system that may be undergoing aging. So to that end, we know that damage can only increase for materials. It doesn't decrease. So this is a statement of the second law. So this statement here is that if entropy is changing greater than zero, we're degrading. The system is degrading when we talk about the system. If it's equal to zero, then that could be like a reversible process. It's not degrading. We'll get into that a little bit more. So the disorder must increase between the system and the environment. For any process, the overall exchange between the system and the environment requires that the entropy generated be greater than zero for an irreversible process and equal to zero for a reversible process. So now we're starting talking about irreversible and reversible. So what do these things mean? I think it's basically what you think they mean. It's if you are creating fatigue in a product, that's not going to cure itself. So it's irreversible. Where if you're in the elastic limit, if you are just bending something just a tiny bit, you might think of that as a reversible process. It's a slow varying, easy to get back to where we were or where we started. No damage is caused. So when we talk about irreversibility and reversibility, in the physics of failure sense, we're really talking about whether we did entropy damage. So to this end, because we talk about the environment, the system, the change of the system plus the change in the environment must be greater than or equal to zero, the entropy generated in the process. So again, another statement of the second law, or another equation statement. So aging causes order in the system to decrease and causing damage. Now, I don't want to lose my audience. We will get to the practical side of physics of failure. But on the other hand, we don't want to play tennis with a net down. So I'm trying to order things and try to make things logical and palatable for the people interested in the thermodynamics, and then we will get to the physics of failure side and where the science becomes applicable. So this might take a little bit longer than I originally thought, but we will get to it. So the total order of the system plus the environment tends to decrease. There's a loss of the order. It equates to increase in entropy, which is our disorder. Now, another thing to note is that not all entropy increase causes damage. So, for example, adding or removing heat increases or decreases entropy, yet the device damage may not occur. So the spontaneous processes creating disorder are irreversible. Example, like a steel beam will corrode. That's an irreversible, and more disorder is being caused. The steel was very ordered, and it corroded, becomes disordered. So the original order created in the manufacturing process diminishes in a random manner and becomes measurable. So, and we're going to talk about how to measure disorder and in a more friendly way than just looking at measuring entropy. So, but the terminology all this stuff is somewhat related. So we can also, so now we know that there's a non-damage and a damage entropy. So we can write entropy change in terms of non-damage and damage. So the in the physics of failure sense, there's some damage that's occurring, and there's some non-damage heating that might be occurring. So stuff that's not causing damage. So you can think of it that you can break it up in parts. And if we include the environment, we can write the statement of the second law. Again, that this whole process that generates this disorder between the system and the environment has to be greater than or equal to 0. And again, the second law can also be phrased by just the entropy damage increase. So those are statements, or physics of failure statements, for what we call damage and irreversible processes. Now, entropy damage can have a threshold, so we want to look at that. A simpler way to look at that, when we talk about an elastic, like metals, when we cause produce a stress on a metal and we elongate it a little bit, it might spring back to its original shape, and no yielding was created, no permanent length change was created. So in that sense, there's a threshold, and we cannot really measure the damage. So whether you're worrying about, well, was there some damage or not, let's not worry about that. Let's just say that if we can't measure it, damage hasn't been caused. So when we go past the yield point, now we're causing a permanent deformation, and that is we can measure that damage. Similar with fatigue limit. So when we talk about fatigue, like aluminum doesn't have a fatigue limit. As we the more cycles we do, we are causing damage, and there's cycles to failure at all stress levels. But for steel, there's a 30 ksi limit, and below that limit, you can do a lot of cycles, and you won't cause any damage or any measurable damage. So we can see that sometimes we have to think about that threshold. Now, a very important thing to start understanding what's going on in materials is to realize that entropy damage can be summed. So the total damage, entropy damage of a system is equal to the sum of the entropies of the parts. This is an incredibly important statement, although it's seemingly obvious. If we can keep tabs on the total entropy over time, we can determine if aging is occurring even in complex systems. So there's our challenge. Can we measure this increase in entropy that's occurring in our system? It may be a complex system, it might be simple like a resistor. And again, for the reliability engineer concerned with the word system, of course there's some exceptions if we talk about redundancy or something like that, but here we are talking about non-redundant we're just talking about a system that's aging, so we're not going to worry about that kind of terminology. Now, let's start to look at how we can measure entropy and make sense out of it, and start talking about more useful things that we can come up with a formula for. So we'll talk about minus fatigue rule. So consider a metal defect which is accumulating during cyclic fatigue in a metal. You can visualize it this way. You can see the little defects in the dots here that are increasing over time. And so we have some entropy damage that's accumulating. And I could be for different stress levels. So if we could count this, if we could count these dots, we would have a measure of the entropy damage that's occurring. We could, we would have a measure of that. So let's say we have M cells, total cells that are entropy damage. And let's say that we need M, capital M, total cells of potential damage to cause failure. So there's a difference between causing damage and causing failure. So we know that things can degrade and they can still perform their task. But at some point, we're going to get breakage of the part and we cause damage. So the cycles that is being created, let's say we're doing n cycles of fatigue. So we're bending something back and forth. And we're creating, let's look at this guy first. So we're doing n cycles back and forth. And somewhere in the material, we're causing m dislocations. And there's some proportionality constant that will be, here we're using a linear relationship. And that's given the constant by F. And the I is for the stress level. So that would change for different stress levels. We would cause more damage for different cycles at a higher stress level. Now, the cycles to failure would be the same. And so this, we would think that the constant Fi would be the same for the same stress levels for these two equations. So when we try to accumulate what we call damage, damage is always when we talk about damage, we're going to talk about a ratio. So it's the maximum entropy, so that's a maximum disorder where failure occurs, to how much we've caused at some n cycles. And we just wrote this formula, so we just have to substitute it in. And the f's will cancel out if we partition that out. And we come up with what is called minus rule, which is the number of cycles that we do over the number of cycles to failure. And so this is a practical rule that people are using. And minus rule is a number between 0 and 1. So that's an assessment of our damage. So we've derived Miner's rule, which was a empirical kind of equation that Miner came up with. That was his value. And we now start to understand the concept of cumulative damage and how we're determining it. As an example, let's say we have an aluminum alloy, and we do, at stress level 1, we do 45 cycles. At stress level 2, we do 310 cycles. And stress level 3, we do 12,400 cycles. How many times can we do this sequence? If we do 5 cycles at stress level 1, 60 at stress level 2, and 495 at stress level 3. So the fractions of life exhausted in each cycle type we can take as a ratio. This is what we would do for stress level 1. That would be 5 over the 45. At stress level 2, it would be 60 over 310, and that would be 0.194. The other one was 0.11, and this should be subscript 3. Sorry about that. So then we can add those up, and we get 0.345, and that's with the so we've done about 34% damage in the material, but it can still perform its intended function even though damage is accumulating. We do this about 2.9 times before we get breakage. So there's an example. And we can extend this Miner's rule. It's a very useful rule. We can extend it to secondary batteries and whatever you feel is applicable. As a reference for a paper on that here, if you're interested, and the stress level would be related to depth of discharge rather than how far we'd be bending the, say, a paper clip back and forth. Now, we want to extend the cumulative damage concept, and because most people apply it or think of it, most people think of it in terms of fatigue, cyclic damage, but it doesn't have to be cyclic damage. We can be accumulating damage in other processes as well. non-cyclic processes. Um, so, for example, just running current through a resistor, if we're overheating it and the resistor is degrading over time, its resistance is increasing, it's becoming more disordered. So, cumulative damage is not, it doesn't have its proprietary, there's no proprietary saying that we have to use it for cumulative damage. So, what I've done is we're writing the cumulative damage, and we bring it to a power because we're trying to make a general statement for a physics of failure aging law. And so not all processes age linearly, so the exponent p has to be added for a generalized case. So for example, we'll see that creep is between p is between 0 and 1, and we talk about where we will see that p equals 1. These are some examples of things that are not cyclic, for example. So we'll get to there. Now, before I go down the path of entropy and you feel that all the entropy has to increase in the universe, there's a concept that I spent some time on. I have a chapter on. I call it negative entropy. And it's a useful concept because we talk about order versus disorder. It's nice to know that there are things that can become more ordered. So we know that aging is a tendency for disorder entropy to increase due to the environmental stress. We now ask the question, is there negative entropy? So we can say, well, what about repair? When we repair something, we're bringing order back to it. How about life forms? Life form goes through growth, and life can actually, when we injure ourselves, our bodies will repair itself. So there's also a kind of a concept of spontaneous negative entropy. So I discussed this. We don't have time in the seminar today, but I do want people to realize that that you can have spontaneous negative entropy, and it doesn't violate the second law, and that's discussed in the book. It's outside the scope of this talk. So, but we can think about it. We would live forever if you think about it, if we had perfect repair. So that's something that you might want to think about. And you want to be careful with irreversibilities, in your own life. Try to stay away from those, and permanent damage that you do to yourself. So these are some of the concepts of that are helpful in thermodynamics when we talk about engines, or we talk about a person, because there's a human engine. We're all very cyclic in some ways, and so we can think of ourselves as an engine, and there's differences between human beings and materials. Now, enough said on that. Let's talk about understanding thermodynamic work, because this is where we start getting more practical on how it relates to degradation. So now I'd like to introduce the concept of free energy in work, and this is a very important concept, free energy. So some of this thermodynamic stuff is very powerful and is incredibly applicable to degradation. The fact that the science hasn't been exposed more to the degradation thing is interesting. But here we are. Hopefully people will grab this, and I think this is an area that will eventually explode in people will start getting into it. So a lot of us are very interested we know some physics terms. We know potential energy and kinetic energy. So if you're rusty on that, if you raise a ball up to a certain height, you're creating what's called potential energy, because now you can drop it and convert that energy. You've done some lifting, and you've imparted some energy to the ball, and now you're dropping it, and that energy is being converted to motion, which is kinetic energy, and of course gravity. You're working against gravity. So in the same sense, when we manufacture a system, the system has a certain amount of free energy. It's like potential energy. It's like we raise the ball. We've created a very ordered system. So prior to aging, our system has a certain portion of its energy that's available to do what we call as useful work. This is called the thermodynamic free energy. So that's a way of categorizing our useful work. So the thermodynamic free energy is the internal energy minus the energy that it cannot be used to create work. So it's kind of like similar to dropping a ball and converting PE to KE. We are converting, in a sense, free energy of a product into work and damage. So you can think of it that way. So the work that can be done on or by the system is bounded by the free energy. So the change in the free energy of the system, so the free energy, so the work that we can do is less than the free energy of the system that's available for useful work. So we know we would say that if we could get the maximum amount of work, it might be equal to it. So the system's free energy is, and what happens during aging is that the free energy of the system degrades. So the free energy is at its lowest state. Then the system is in equilibrium. When the free energy is in its lowest state for the system, then the system is in equilibrium with the environment. So the change in the free energy is zero. So as well, the entropy, which is the disorder, is maximum. We created the maximum amount of disorder, and we have the minimum amount of free energy. So from that sense, we are in equilibrium with the environment because no more damage can be done, but we can't get any more work out either. So at that point, the change in the free energy or the change in the entropy is zero. So we begin to see that we begin to understand ways of categorizing materials in some ways. The change in the free energy, F, is related to the entropy and the work. So here we are. We can write the work in terms of free energy and the damage that's caused. So this is a thermodynamic kind of expression. And you don't have to worry about it too much because it's not going to be something that we're going to be using per se. We're going to be using the concept of it. But you should know that if we had the maximum amount of work, it would be equal to the total change of the free energy that we could do on the system. That would be the reversible work. We can talk about it in that terms. So the actual work that we can get out is the reversible work minus the irreversible work. So this is our damage. So we begin to see that the thermodynamic work is perhaps the most direct measurable, and practical quantity to use to assess a system's free energy. And why do we care about the free energy? Let's talk about it again. The free energy is the maximum amount of useful work we can get out of a system. And after all, that's the bottom line. We want to know how much cycles to failure. How can we get stuff? How much work are we going to get out of this before this wheel falls off or this transistor falls apart? So that's what we're talking about. So yes, it's a new platform, but let's give it a try, and let's take it to where what we're talking about. Let's see what we get out of this in terms of usefulness. So let's look at reversible work and free energy. If the system's initial free energy is denoted by the subscript I before aging, and the final free energy is denoted by subscript F after aging for final, then we know that the initial is greater than the final, of course, and the reversible work is the maximum change of the initial minus the final. So there you go. And of course, if we want to dot our I's and cross our T's, we can talk about constant temperatures and things like that in thermodynamic terms. But in terms of what we want to talk about usefulness, so there you have one of the most important concepts. And what does this say? Let's sort of summarize this by some equations. Why not? So let's have some aging equations, and we can write aging equations. We say that we're in a non-equilibrium state where we're in an aging state if over time the entropy is increasing or the free energy is decreasing. So we can talk about entropy increase or free energy decrease. When there's no more change of entropy or no more change of free energy over time, and the entropy is maximum, large as possible, and the free energy is small as possible, we're in a non-aging state. The part is basically broken. Not going to get any more useful work out of it. So again, actual and irreversible work. When damage occurs, this reduces the maximum work. Damage occurring during the work process on or by the system is called irreversible work. Then the actual work that can be done on or by the system after some irreversible work occurred, we can look at that change. So the actual work over time that's changing is really given by how much irreversibility is changing over time. So we know that damage causes a loss of ability to do useful work. Disorder also equates to decrease in free energy. So loss of the ability to do useful work. The free energy is bounded by that work. So there's different ways that the free energy can change. So it might be a smooth, simple downhill ride all the way, or it might come to a sort of a quasi-minimum, and we might have to scale a little bit of barrier. And this is kind of when we talk about Arrhenius law, and we have to overcome a barrier, and we can think about disorder or dislocations and how they're created when we heat something up, and metal is becoming more disordered, and we are causing damage by heat. It has to jump over a certain barrier, so dislocations are created. So in this case, if the free energy looks like this, we're jumping over a barrier. Another dislocation occurred. So that's how we would think of it. So here's a thought. I thought I'd throw this out there. A category that is not used much to categorize materials. Would we need the SN curves if we knew a material's free energy? Well, there's a thought. So I just thought I'd put that out there in the seminar for you, because everybody's using SN curves, but what if we just knew a material's free energy? Couldn't we create the SN curves and stuff like that? So this is something you might ponder over. So the relationship between work and damage. So define damage through work. When an environment does work on a system, the work that causes aging we call damage, and can quantify it. So damage, we sort of started seeing this when we derived it before. We think damage is typically done a number between 0 and 1. So it's the maximum work to failure divided by the partial work that we've done. And that's the practical way of doing this. So this is where we're starting to get the practicality of the physics of failure. The total work is a good measure of the effective damage, as we cannot always measure damage itself. We can't go into the crystal lattice and know how many dislocations we've caused. And on the same token, in order to do good physics of failure details, if we want to assess it, we have to know our stresses and our path that we're taking. After all, there's a number of ways to climb a mountain. And so you can do it with a backpack on and become more stressful and more energy, or you can just, go up in a car. And depends on the path that you take and the endpoints. So now let's get into a thing like the energy approach that I talked about in my summary. We're going to talk about conjugate work. We stated that thermodynamic work is perhaps the most direct, measurable, and practical quantity to use in assessing a system's free energy. We can now use a thing called conjugate work, because we want to categorize things and be able to do it on lots of different, we want to come up with physics failure laws on different things. So we can now use conjugate work as an energy approach to assess damage, both cyclic and non-cyclic, over time, to improve methods for solving physics of failure problems, finding acceleration factors, and assessing damage. So we can sum the work, and because it's a useful quantity, and we can sum it in terms. So what is work in terms of the physics of it? Well, work is a force times a distance. So if you go in your physics books and you look at work, it's just force times distance, and you can sum it up over your stress levels and however you want to do it over the work path that you're looking at. So again, we have to be concerned about the path that we're taking. So it looks kind of complicated, but basically what I'm saying is we're just doing work equals force times distance. So don't get too turned off by this. And the beauty of it is we can apply it not just to, say, mechanical wire tension stretching out, but we can apply it to lots of areas. Because we can think of, once we know how this method works, that work is equal to force times distance, we can talk about generalized displacements, generalized force, and so I've made a table here. This is the kind of table that you want to look at, and the kind of quantities that you want to look at, depending upon your particular physics of failure problem, and how you would go about coming up with physics of failure laws based on your particular problem. You would go to the area and try to understand what are the characteristics, the generalized force and the generalized displacements. So once we basically know how to solve a physics of failure problem, we can start thinking about solving it in other areas. So let's get a little bit more to it. So we got both cyclic damage and non-cyclic damage. So here's our most accurate kind of expression. I mean, people use Miner's rule, but the reality is Miner's rule is an approximation because, as you're bending a paperclip back and forth a certain distance, a certain stress level, you're actually causing dislocations, and it's becoming easier to bend the paperclip back and forth. So stresses, the things are changing in a nonlinear way. So this is the most accurate way of writing it for cyclic damage, and we can do the same thing for non-cyclic damage. So and we have to be careful about the path that we're taking. So we have to integrate over the right path. So plastic work causes damage. That's a mechanical term. That's basically nonlinearities. When if you're in the elastic region, they call that elastic, and you're not causing damage. But once you start causing damage, you're bending the paperclip back and forth, and you're starting to deform it. That's some plastic work. So we need to, when we do cyclic damage, we need to sum up around the stress strain, so the work area. So that would be the most accurate way of doing it. So we can't always do that, but we could, sometimes we have strain gauges and we can do this. And sometimes we can't. That's why Miner's rule comes in and is a very convenient way, because we can't always do this sum and be that accurate. But if we could, this would be the way to go. So let's see where a little bit more about Miner's rule. We can derive it in another way. So here, let's use the work approach rather than counting dislocations that we did before. So we know that work is a function of stress and the number of cycles. So we can make an approximation that we can pull out the n. So that's where some of the Miner's rule approximation comes from. So this S is related to n, but we take it out. We're making that approximation. It should be an approximation sign here. But so when we do the damage, we have different stress levels, and this is the work to failure. So we can divvy this up, and we can see that the work to failure has the same amount of energy. So the work cancels out for the stress, and we get Miner's rule. So that's a work approach for assessing that. So this would be the total work that we did on that. So we can now modify Miner's rule a bit, and because we come up with a thing called acceleration factors between different stress levels. So when we do that, so if we're doing everything relative to stress level 1, then what we can do at stress level 2, we can relate it to stress level 1 cycles, and we can figure out how many cycles. This would be the total cycles at stress level 2. So obviously N2 equals this acceleration factor times N1. The same with n3. Capital N3 would equal this acceleration factor times n1. So that's how we would take minus rule and use acceleration factors. Now, another thing that's important is we have to come up with a way to come up with acceleration factors. So the way that I do that is I say that most of the time, things are time and the distance coordinates and the force coordinates a lot of times are separable. So we can separate out time from the force and distance coordinates. And this is a very common case, and we'll see that. So damage between two different environmental stresses, so Y1 and Y2. The failure occurs for each time tau1 and tau2. Then the damage values. So in other words, let me start over again here. If we have damage between two different stress levels, so let's say we can actually separate this out. We're going to use capital tau as the time that it takes to cause failure at stress level 2, because we're going to say the damage is equal to 1. And when damage equals 1, that's when we have failure. So this is the time to failure, and this is at stress level 2, and this is the time to failure at stress level 1. So now, when we ratio that, when we solve for that, this becomes our acceleration factor between 1 and 2. So then damage can be written, when we write damage like that, we can start thinking about writing damage with the acceleration factors just like we did minus rule earlier for here. So that's how we would do that. So again, this is the time, this would be the time to failure tau, and small t would be the amount of time that we've done so far. So that's how we would write that. So let's look at some selected physics of failure models and see how this applicable science evolves. So let's start off with something that's linear. And what I've done is I've used what's called Archer's Wear equation, and this is a form of it. So a lot of people may not be familiar with wear. So let me just introduce the equation so you get a concept for it. But if you look up how to look about wear, you say, well, how do I figure out how much damage I'm doing when I'm doing wear and damage to failure? So that's what we're asking the question. So we look at Archer's. We're saying, let's say that this thing called Archer's Wear equation is applicable to our particular problem. You'd have to use, there's a number of different Wear equations in the literature, so you'd have to use the one that had to do with your particular problem to come up with the physics of failure method and understand the acceleration factors for this and stuff like that. Because we want to understand wear, we want to understand what accelerates it, we want to know, is it linear, is it nonlinear, things like that. So the wear depth is d. K is I think it's called the Archer's Wear constant. P is that weight. So what does this make sense? The more weight we would have, the more wear depth we would create. Yeah, that makes sense. L is the length. So L is the sliding distance. So the more distance that we would slide, yeah, the more wear we would get. If we have a bigger area, this covers a bigger area, same weight, no, it would not go as the area. The larger the area, the smaller the wear depth. And H is the hardness. The harder the material, the less wear we would get. So we see that this is a pretty practical equation, and we begin to understand it. So it's not that magical. I'm not trying to lose anybody, so I'd like people to know what's going on. So now we're going to use that external work goes into creating sliding distance and causing wear. So we're going to use this work equals force times distance. So there's our force, the weight, and the distance, sliding distance kind of stuff. So we're going to use a constant here for the W, and we're going to use a constant for the distance. We're not going to worry about the constant right away. And the sliding distance per unit time, so that's velocity. So we begin to see that. And now we make a substitution in for Archer's wear equation. For that, we could enter the sliding distance or the velocity. So we come up with this expression right here. So then the damage would be related to that, and we would have Archer's wear equation relative to that. So this would be time, the time to failure, and this is the time that we did so far. And so we would see that can be simplified because some of the constants drop out, the Archer's wear constant and stuff like that. So it's dependent upon the velocity when we write it this way, the time, the area, and the weight. So this tells us what the things are, stuff like that. And to take this a little further, we want to say, well, what is the damage when damage equals 1? We can start coming up with an acceleration factor. I'm sorry, I didn't write that properly. So when the damage equals 1, it would be we would relate these. We would put tau here and tau 1 and tau 2 here, and we would come up with the acceleration factor as we were talking about before. And there would be our acceleration factors. And one of the things you notice is the acceleration factor is a function of the weight and the velocity, inversely proportional to the area. So, but there's no exponent, so it's not like a power law. So, unfortunately, wear is not easily accelerated. It's kind of like a linear thing. So, here's another thing we have is called the cast equation, which I introduced for wear. We talked about this equation right here. It's linear, and we can write that in. And when we put that in, when we put the acceleration factor in for wear, it becomes the wear damage acceleration factor equation. And I call it the cast equation. It's the cumulative accelerated stress test equation for wear. So I've tried to simplify some of this right here, and perhaps I did it too much. I think the more detail in my book. Sorry about that. So I think there's some missing steps in there. But anyway, you get the idea. Let's look at another example. A lot of people use the Arrhenius expression. If we have a corrosion current, for example, here we have the current and it's thermally activated. And generally, the rate of the reaction is given by that Arrhenius expression. And then the time t1 and time t2, they are related by the acceleration factor. We're familiar with that. So if we had the damage, so let's say we wrote the damage as the voltage potential times the current, because that would be related to the work. And that's what was one of the equations. I don't want to go back to that slide. I think it's basically related to that. I think there's a little more detail in that. And then the time involved, and we can take the ratio of that, and we come up with the acceleration factor for that. So this is a little more familiarity with some people, because people are familiar with the Arrhenius acceleration factor. And we can write the cast equation, it's cumulative accelerated stress equation. And we're going to see how to use this in a second. It's an incredibly important and very useful equation. So we wrote that. So we can when the damage equals 1. Let's see. Did I write that right? Doesn't quite look right to me. Did I have that? I'm not sure why I put the damage equals 1 there. Oh, not quite sure what I've written there. I guess when the damage equals 1 and you have failure, you can bring out the tau here for that time. And let's look at an example of this, of the Arrhenius acceleration factor for testing. So how long do we have to perform a high temperature operating life test at 150 degrees to simulate 10 years at 70 degrees and assume an activation energy 0.7 eV? So we can write that. We have to put things in terms of degrees Kelvin, and we come up with an acceleration factor of 88. We want the lifetime is 10 years, so that's 8760 hours divided by that acceleration factor. So we'd have to test for 1,000 hours for that if we were testing at 150 degrees C, and the actual use condition was 70 degrees C. So let's use an example using the CAST equation and see why that is useful. So this cumulative accelerated stress equation, we wish to accelerate stress test a unit at 100 degrees C to equate to 10 years. How many hours do we test for? Now we have a little caveat here. The use condition is not straightforward. 20 degrees C in use condition occurs 50% of the time. 40 degrees C occurs 25% of the time. And 60 degrees C occurs, say, 25% of the time. We're going to use that Arrhenius model with a 0.7 EV. So how long do we test for, knowing all that? So first we would come up with the acceleration factors for each stress temperature relative to our maximum, our 100 degree test stress. So 20 to 100, that's 380. 40 to 100, that's 64, and 60 to 100, it's 13. So obviously there's 60 degrees, you wouldn't have as much acceleration factor compared to 20 degrees C. So this is kind of making sense. Now we use that CAST equation here, and we write it out. It was 43,800 would be the percentage of the time of 10 years that we were at, let's see, 380, that we were at 20 degrees, and 21,900 would be for 65, I don't know why I put 65 right here for this acceleration factor, so we'd be at 40 degrees C for 40 degrees, 25% of the time. So 25% of 10 years, I guess is what we're saying, is that, and 25% of 10 years is this. So then we would add that up, and we get 2,000 hours for our test. So then we need to perform an accelerated test at 100 degrees C for 2,057 hours. This will equate to 10 years of life for this environmental profile. So this is what I call environmental profiling. I'd just like to bring out another degradation model that I think is very relevant for a lot of times people don't do, they want to make predictions, so you're modeling things. One of the more useful models that occurs in the literature is what I call log time aging. Like creep wear, it's applicable in different areas. Bipolar transistor aging, beta. Not certain wear models. It could be applicable, but this is the form of it. There's a lot of aging in the beginning, and then there's less aging. So a lot of change in the beginning. Say it was creep. You get a lot of with a weight on a wire. So you put a weight on a wire, and in an early time period, you get a lot of strain, so elongation change, and then later in time you don't get as much. So that's kind of the log thing. And you can also write this as a power law, but the actual physics comes out to a log time law, and that's in the book. So if you're interested in a more detailed analysis on the actual physics of it. Now, just corrosion requirements. Requires the following: an anode, a cathode, an electrolyte, and a conductive path. Though if you take away any one of these, if you remove any one of those, corrosion will be stopped. And the corrosion current is not well defined, but it's proportional to the rate kinetics and this local relative humidity. So this is the basic form of the equation for the corrosion equation, and we can, in more detail, the reason for this is in the book. If you're looking for more details for this, the chemistry behind it. So, but the point is that you can come up with an acceleration factor over with the ratioing those stress currents related to the damage. So you get a damage acceleration factor for humidity and temperature. An example for temperature, humidity, acceleration. What is the equivalent time for 10-year life test for a use environment at 40% relative humidity and 25 degrees C, when the accelerated test is 85% and 85 degrees C? So we're going to use for this power exponent 2.66, which is a common constant to use, and for the activation energy 0.7. So first we do the temperature acceleration factor is 96, and not sure what happened to the humidity part. So there's a mistake here, so sorry about that. Oh, there it is right here. It's right in front of me. There's the humidity part, 7.46. So we multiply the 96 times 7.46, the 10 years, we have a 130-hour test. So I guess I'm going to kind of hurry up. We're kind of going over here. There's a few more things that I want to get to. So on the creep, we can do the same kind of analysis, the creep equation, and we can come up with a cast equation for that. For thermal fatigue, we can do the same kind of analysis, and you can come up with the cast equation for that. Vibration, you can do the same similar analysis for that, and you can come up with the what I call the cast equations for that. Here's a summary of the cast equations for those cumulative accelerated stress and the damage that you would get, and how to environmental profile. Heat engines, I'm going to go through this pretty fast. Basically, on a heat engine, the heat in, we convert the heat in to work, and then we expel heat. So that change is the work that's performed that we expel out. So work is converted from the heat. And we can start thinking of efficiency. How much work out do we get for heat in? So that's one way to look at that. And we put this in and we get this equation here. Electrical engines are more efficient. And we can start to realize that the efficiency, when we talk about that, when we talk about engine work around the force and distance equation for the cyclic engine, we can look at the efficiencies changes or the work that we've done. We can compare it to a new engine versus a degraded engine. We can think of it that way, and so it becomes kind of similar to what we had before. So in a similar way to what we had before for damage, we can look at the changes in the efficiency for a reversible versus an irreversible situation for the engines. Now let me talk about a little bit about noise and its value as a physics of failure tool. So what is noise? Noise is caused by some sort of disorder in the system, the results of what causes variation in the operating process. Noise does not always have to be acoustic. So there's in the physics world, noise is related to the some oddity about the system that like a variance, and it's measurable. So in terms of aging, if we have an operating system and our system is degrading, as we put energy in and we get energy out, the energy gets disrupted. So we know that that disruption is a signature of the disorder that is occurring. But how to measure that, and what does that mean? Sometimes it's easy to measure, and sometimes it's not so easy. It's very subtle. For example, let's say it's a transistor, and there's power loss. Okay, not a big deal. We can measure power loss. We don't have to worry about some refined measurement. But sometimes we want to have a better measurement system, because a lot of times you cannot see the damage that's occurring by something simple like power loss. There's things that are occurring and the damage that's increasing in the system, and you don't always, things can a lot of times things can perform their intended function while they're degrading, and you have no idea of the damage that's going on inside the material or to the system. And all of a sudden, it fails. So how do we measure that's occurring? So the way that I present this in the book is I call it mesoscopic noise entropy measurement. So just an idea where, not to get into semantics too much, but mesoscopic's not microscopic, it's not macroscopic, it's somewhere in between. So it gets a little hairy here, but when we talk about figuring out what's called the differential entropy, but the result is really interesting. If we're looking at a Gaussian white noise that's occurrence, the entropy change goes as the variance. So it's not going to go as the amplitude; it's going to go as the variance for a white noise system. So I'm going to have to get to a problem for this, otherwise it's going to seem a little too complicated. To clarify, for a Gaussian noise system, the differential entropy is only a function of the variance. For a system that is degrading by becoming noisier over time, the entropy damage can be measured in a number of ways where the change in the entropy is related to that variance. So let's say we have an engine. Engine exhibits a constant power spectral density characteristics. Let's say it's 3G RMS content in a simple bandwidth between 10 and 500 hertz. Then the engine degrades. It goes, say, if it's a car engine and it goes on a long trip. You come back and you make another measurement. Now we have to make the measurement path the same. So we make the same measurement path and we measure it again, M2, and now it's exhibiting noise of 5G RMS content, and this is somewhat similar to the noise that we would measure. And we can see the damage that is being exhibited as a factor. Here I made it greater than 1 in this particular case because we're talking about entropy, but you could invert that to get it to be a number between 0 and 1. So that would be the damage that's caused. And this is actually what we see a lot of times in vibration spectra. Now, how about human heart? Let's look at something more subtle, something that we cannot see by the power of a transistor degrading. Something that's occurring that's very subtle. We're talking about congestive heart failure, and because there's not a lot of interest, there's not a lot of examples in the literature. People are not using noise as a reliability measurement, and I'm making the case that you should. So look at what's being done, what these authors have done, and I cite that. Let me see if I cite that. Sorry, I don't have the citation here, but it's in a paper I wrote and also in the book. Anyway, if you look at elderly people and young people, the noise that is observed is very similar. But for patients with congestive heart failure, something that you cannot tell by listening to a person's pulse, by looking at their variance, that variance is actually, if you look at that variance, you will see these authors were able to detect the congestive heart failure. So that's a very useful measurement. I make the case here on this slide that we shouldn't just look at global warming. There's other metrics, this other metric of volatility, extreme temperature swings. Now, our environment is very, we take things on average a lot. We look at the average temperature, the average this and that. We can think of it as Gaussian. And that spread, a lot of people in the weather area, they don't increase that spread. But our weather is becoming much more volatile, as well as global warming. So this would be the prediction of what that would mean for our global warming effect. So noise is a very important physics of failure measurement. Lastly, I'd like to end up by my final thoughts on the theory of organization. So after all, we've been talking about disorder and aging. So the theory of organization for stability, reliability, and quality For a system, subsystem, or component, materials or processes in general, the higher the organization, the more likely is the probability of success. So in the thermodynamics things, this is the equation for disorder, entropy increase. So if we seek to maximize the system's free energy, minimize the variables in the system or process. So the variability is something that we want to look at and worry about. Variability is related to the probability to fill the disordered state. It is a strong measure of disorder. Example, crystals are highly repetitive structures like metals and diamonds, and they're strongest materials, and they're most reliable. The free energy capability to perform useful work is higher than, say, amorphous materials. So the theory of organization is about reducing disorder, becoming with smart designs, trying to order things in a higher degree. So smart designs in manufacturing, preventing failure requires a reasonable measure of organization in materials, designs, manufacturing, and even the way you organize your organization for your group. So the higher the probability of success. So I just thought I would end that because everything we're talking about is disorder. So I thought I'd talk about order. So again, I did just if you cite this work, if you please cite my material here, and if you have questions, obviously we went through quite things pretty fast, and I probably abbreviated some of the derivations, so some of the things were missing, and so you can get in touch with me if you wanted more details, and of course there's more details in the book and things like that. So I hope you enjoyed the talk. There's my biography and stuff. So if you have any questions, I guess we take them at this time.
Thank you, Dr. Feinberg. It was a very informative presentation. And to the audience, a note, you can post your questions in the questions tab. And if we run out of time, then you can, and if you still need more questions to be answered, you can still email Dr. Feinberg. He has posted his email address over there. So I guess some questions are starting to come. So a comment from Kim. I can follow the work and free energy considerations, but it's still a bit fluffy and hard to understand. How can it replace the essentials? The essentials are very easy to understand with respect to unit of stress and number of cycles to failure, whereas I cannot figure out how to find or set a figure for work to failure for a certain material.
Yeah, the work to failure, the concept of the work to failure was really all about coming up with the physics of failure aging law. So basically, what you need to do is you need to come up with your physics of failure law. If like we talk about wear, this Archer's wear equation, and then we came up with a damage expression for that, and the damage expression helps to give us the acceleration factors. Because after all, we don't have an acceleration factor for wear, but now you do. If the Archibald's wear equation applies. So it's a method of finding the physics of failure aging law of interest related to the physics behind the aging event. So you have to think of it that way. I hope that helped to answer the question.
The next question is from John Fisher. So you showed an example of an accelerated test developed using a fast equation with a system that had a non-constant normal use condition. How does this numerical result computed with this method compare to the standard Arrhenius method?
Could you say the last part? How does it compare to what?
Compared to the standard Arrhenius method.
The standard what?
Arrhenius method.
I can't. I can't really understand the last three words. RS.
The Arrhenius method. Arrhenius method. Sorry, I might be pronouncing it wrong. ARSENIUS. The method which you have it in one of your slides. The standard method to.
I'm really sorry. I can't understand Um, so this is the way that you could do environmental profiling, and this would be the logical way using that acceleration factor. So there's no comparison. This is the actual if the acceleration factor applies, if that if we for example if this is the equation that you're using, then the cast equation is applicable.
So, so Dr. Feinberg, I mean, relating to that question, he's asking how does the result computed with this method compare to the ordinary method which you have in your plan?
Yeah, I'm really sorry. I can't figure out what.
Okay. Okay.
Yeah.
Fine. Okay. Moving to the next question. How does the order or disorder in your theory of organization relate to the robust design of products and process?
Yeah, I guess I'm not hearing you very well. I can't. It's really hard to answer the questions when I can't understand. Sorry. Maybe you could
Oh,
just speak slower.
I'm sorry. Looks like my volume is really bad, Dave. Are you there to take the question?
Yeah, I can help out here. What question were you on?
I'm on, say, question at 112, if you have the time.
Yeah, what was the timestamp on the question? I can.
112,
What's the timestamp on the question?
112.
112.
Yeah.
So how does order and disorder in your theory of organization relate to robust design of product and process?
I think that's a really nice question. So I tried to spend some time on uh, order and disorder because you can talk about disorder and aging, but you can also talk about order and how the probability for success. So there, you can think about the fact that you'll be much more successful with your products if you try to have a more ordered design. So, like even when you're designing a circuit board, if the circuit board is not well ordered, if things are not put into place, if things are, you know, uh, if you don't take care about how you order your components and manage your heat flow and things like that, your probability of success is maybe not maximized. You might look at your circuit board design and you could say, well, can I order that better to maximize my ability for this design to be successful? So I think that's kind of what I'm saying on that last slide, and it's an excellent question. I really do think there's a lot more room for developing the theory of organization. I think it's an interesting subject in itself. So I don't know if I can say much more on it, but I think you have to take into consideration variability, stuff like that. I mean, we know a lot about these things, and a lot of people use them all the time. We talk about variability in products and try to get the variability out. And I think these are excellent thoughts, and we're maybe trying to take this to another. I don't know if another level, but just another way of saying it.
Yeah, we're about 19 minutes over. One more question before we let you go, Alec. What kind of model can we use to predict the failure in insulations related to electrical items?
So uh, insulation breakdown is dielectric breakdown. So I think I'm looking at that's a that that model there. Uh, I have there are models for dielectric breakdown. So it would be related to dielectric breakdown. It's like not off the top of my head. There's a number of um, it's usually I think there's an exponential model for voltage breakdown, stuff like that. So you would use that model and come up with use that equation for that.
Okay, great. Well, I see we're at the end, so I think we've lost pretty much half of our audience. So we'll end the webinar here. This is a recorded session, so it will be available at astqrd.org. And we'd like to thank our presenter, Dr. Alex Feinberg, on behalf of the AS2 Reliability Division and on behalf of our audience for presenting today. And we hope that you'll come back in the future and do another presentation for us.
Thank you, everybody.